Hey Steve, it is May 4th. May the 4th be with you. 2017. Time is 16:47. Temperature is 45 degrees out. And it's raining again. Yay! Anyway, I'm going to take a break from the rock type thing I've been doing. I'm going to talk about something else. Geology isn't just looking at rocks all day. That's not what most of us even do. We might spend a couple hours a day doing that, maybe when we get home for fun or whenever, but usually it's not what we do. And geology, like all science, can make predictions. Okay, and I do a lot of geologic mapping. And basically what you do when you geologic map is you go out in the field, you look for outcrops, you take measurements of what's called strike and dip. Strike, by definition, is 2 points of equal elevation. They can be inches apart, as the case we measure them in the field with a burnt compass, or they can be 5 miles apart. It doesn't matter. Dip, by definition, is perpendicular downslope to strike. Okay? Because most rocks are not exactly flat lying. Most of them appear to be, and I'm going to get into that. But first, what does a geologic map look like? Well, you sit there, you take a base map, usually a contour map, and you go out in the field and you make your measurements, your observations, and you draw your lines, and eventually you'll make colors. This is a very simplified geologic map that I came up with, where my strikes, which are the longer line, and that's your orientation, your equal elevation 2 points, and then the dip is the number here. This is really oversimplified. I did this for illustration purposes. Here my strikes are almost all east-west, and my dips are either north or south. So you'll get there, you'll do your little mapping, say this is a transit. I have a scale here somewhere of 1 inch equals 100 meters. And why did I pick 1 inch? Well, because I like mixing metric and standard. Actually, there is a protractor that geologists use that I'm going to show you in a later episode of how we actually do this stuff. I'm going to draw it for you on camera. But, so we've made this. Okay, what do we do with this? Okay, it's information. You can see I've labeled things units. What the units are actually, what geologic formations they are, isn't relevant for this discussion. They're just distinct formations or members within a formation. Well, you do this. This is your map view. Make one of these. A cross section, a slice through the earth to a certain depth. Here, my vertical scale is the same as my horizontal scale. 1 inch equals 100 meters. I did that for simplicity purposes. So this is what your slice would look like. You generate your cross section. Okay, that's what you do. All right, and if you look at this, you'll notice I have on my map no units A or B, but in my cross section I have a unit A and B. Well, how do I know those units are even there? When I did this, quite honestly, I did it just to fill the page. But you can do this. There is justification for this time to time. If you have no indication that unit A or B are here, you would cut your cross section off, and where your dips, because these are your dips, that's how you draw this area right here, you would just sit there and put older than or something like that if you didn't actually know. Okay, now this right here is just a, 1100 meter transit. Okay, and I did throw a couple structures in here. Here's an anticline. This is a fault-induced structure. Here's a fault on the surface. You map it like that, and here you put your arrows, relative movement, up, down direction, based off what you did. Okay, and so my units A and B there, say unit B, since this is only 1100 meters or so, say unit B, another 600 or 700 meters to the north or south, actually crops out its full thickness with unit A, at the bottom of the formation, and unit C or unit B on top of unit C on top of it, and say the thickness is consistent. Okay, if this came back down and up over here, same thing over here, and then A was exposed over here, and so was C. and the thickness was consistent, I can assume that continues in the subsurface. Now this would have to be confirmed with drilling or something like that, and if it is, then my model's legitimate, okay? And unit A, say I don't know the thickness of it, we'll just say it's Precambrian in this example, and what does outcrop is a granite on one side and more of a gneiss with some sort of metaconglomerate on the other side. I can just lump that together into one unit because I don't have determinate evidence of the local area to sit there saying I'll just call it Precambrian undivided. Okay, well, so that's basically your slice, your map view, and your cross section, okay, right there. Well, how do I generate that? Well, like I said, there's a special little protractor that actually works really well to do this. And when I solve, I could always use trigonometry, but the problem with that is it's a lot quicker to do it graphically to scale. And when I took the professional geologist tests, that's what I did. I solved everything graphically. I didn't solve anything mathematically. And I passed both tests first time, which most people don't do. Because if you're proficient with the protractor, you can knock out something like this in under 30 seconds. But if you're sitting there fumbling on a calculator and say you switch a sine or cosine on the PG test, I guarantee you that wrong answer, that flip, is one of those choices. But if you're off a degree or two graphically, they're not going to be that close together. You'll be able to figure out which one it is. But anyway, so I did this as well. Okay, now say this is your outcrop, there's your scale, and this is just an outcrop you're looking at, and these are flat-lying beds. Okay, you can directly measure the thickness of those beds. All right, you have your scale, and it's pretty easy. You just measure how thick they are. Well, if they're not flat-lying, what do you do? Okay, well, say here I am concerned with this limestone unit, and I'll explain what the orange lines are in a minute, but I'm concerned with that limestone unit, and I have my dips, and we'll just say strike is perpendicular to my cross section here, okay, just for the sake of argument and making it easier. Okay, so I'm concerned with that limestone unit mainly. All right, I want to know how it goes into the subsurface, and I want to know, you know, what its thickness is. Well, when we talk about thickness of a rock unit, unless they're laying horizontal, like in this part, that is going to be different. We talk about the thickness of the rock unit. So if it's flat, your thickness is going to be like this. If it's bent, your thickness is going to be over here, if it's been deformed or uplifted or whatever. That's what we mean by thickness of a rock unit. On the ground, but on the ground you don't know that. You're going to make a measurement. Here I put, so here on this side, my limestone unit is, I do my transit and I find out it's 350 meters long. Over here it's 500, and I got my dips from both the top and the bottom of that unit. I construct this with my protractor. Okay, and as you can see, this is that limestone unit graphically represented on both sides. That's this side, that's this side. I don't need to do the middle to get the thickness at the surface, okay? So I draw those lines to scale, horizontal scale equal to vertical scale, and I come up with, so my thickness on this, because my beds, remember, are dipping. So when I'm talking about thickness, this is not my thickness. This is my thickness. Okay? And I come up with 240 meters on one side, 270 on the other side. It's a difference of 30 meters. That's a difference of roughly 10 to 15%. So the limestone is pretty consistent in thickness. So when I draw my cross section, I can continue that thickness, okay? And if you notice here, I did a cross-bedded sandstone, and notice we don't measure cross beds to get the bigger picture because they're very small structures. And as you can see, cross beds, and this has been deformed too, all three of these units have been deformed. So my cross beds look like if I was to measure one of those, that's not the measurement of that formation going like this. That's just the measurement of that crossbed. And if I did that, I would get wacky numbers. That's why you got to find a bedding plane. And most cross-bedded sediments are planar. And the good thing about that, and sandstones tend to be planar. You get tons of different, but planar crossbeds are nice because there's usually, like if they're cross-bedded like this, you usually have actual beds bounded. Might be bigger, but you can still get measurements. And if you take measurements on those and they don't fit the rest of the surrounding data, then you know you screwed up. So, okay, so that is how we determine thickness of a geologic unit. Now what these orange lines are, so I draw this cross section, I submit it to somebody, say whatever, or say I'm working for somebody and they want to put in that limestone unit has a lot of water in it. We don't want to use the overlying sandstone unit, although that would probably make a better aquifer, because say it's got a lot of really heavy minerals in it that would require a lot of like treatment to get out or something like that, or there's towns lying above it, so we got gas and it could potentially be contaminated aquifer, so we want the limestone unit. So I draw them that cross section and they go in to put their wells in, and according to my cross section, these are the depths at which they should, at the end of the orange line over here. Is it upside down? Yeah. Over here, and here. Those are the depths at which they should encounter that limestone along that transit, or along the line of my cross section. And say they do this one over here, which is a prediction of 300 meters they'd have to drill to get to the limestone. And say they come up, they hit it at 299 meters or 303 meters. Was my model correct? Yeah. I mean, it's a minimal distance. Not to mention they'd still have to go deeper into the limestone to actually extract water from it. So that would be a way to validate my prediction. So I think that's all I wanted to talk about today. And sorry it's a long one, but I hope you learned something.